So now that we have derived and understood the relation byx into bxy equals to r square, we can also write r, or your coefficient of correlation, as the square root of the product of the two regression coefficients bxy into byx. Another useful relation to remember, and the same relation can be expressed in a different manner. So we know that the regression coefficient of y on x, byx, is your pxy divided by sigma x square. Remember, we are always writing the variance of the explanatory variable in the denominator. Okay, now what I can do is I can write this as pxy divided by sigma x into sigma x, and I'm gonna multiply sigma y on top, and so I will also multiply sigma y in the denominator. That is, I'm multiplying and dividing by sigma y. So in effect, these two will cancel and I'm left with the same formula as the earlier one, right? So this is just a mathematical manipulation where the value of byx is not changing, right? So how does that help me? It gives me another way of writing or expressing the regression coefficient byx. What I'm going to do is I'm going to group together these three terms so that I can write it as pxy divided by sigma x sigma y into sigma y by sigma x. So like I said, I get another way of expressing the regression coefficient byx in terms of the correlation coefficient r into sigma y by sigma x. This relation is very useful. Remember, the trick to remembering this is byx is the regression of y on x. That is, y is the dependent variable and x is the independent or explanatory variable. So like I was saying, the trick to remember this is the explanatory variable is x, so in the numerator you will have standard deviation of x. In the same spirit and in the same line of logic, you can write the regression coefficient of x on y is r times sigma x by sigma y. Once again, the explanatory variable is y, so the numerator will have standard deviation of y. Now, these two formulas that I have boxed, or relations that I have boxed, as well as the first one, r square is byx into bxy. These three formulas are very useful for solving all sorts of MCQ questions related to regression and statistics. Very useful for your entrance exams, very useful for your net exams, and even for any exam where you have some basic level of statistics. So please do take note of this. They help you solve for answers really quickly. They are shortcuts. And now that you have this relation with you, you can express the regression of y on x, which is given here. This is called regression in deviation form because y minus y bar is deviation from arithmetic mean of y, and x minus x bar is deviation of x from its, that is x's, arithmetic mean. So this relation can be expressed in this format: y minus y bar is equal to r times sigma y by sigma x, and if you have regression of x on y, in the same way you can replace the regression coefficient be xy with r times sigma x by sigma y. So like I mentioned earlier, do remember these relations. They are very helpful and give you quick shortcuts to solve MCQs related to statistics and regression analysis. Now let's have a quick discussion on the properties of the regression line. The first important property is that both the regression line of y on x as well as regression line of x on y will pass through the mean values of x and y. So we'll pass through x bar comma y bar, and this should be obvious by the fact that both your regression functions can be expressed in deviation form. So in the deviation form, you have your x bar and y bar as a part of the equation itself, which would mean that both x bar and y bar are points, or the coordinate x bar comma y bar is a point on both the lines. Now, the slope of the regression line of y on x is byx. This is pretty obvious if you remember that the regression equation is written as y equals to a plus b times x. So y equals to mx plus c. The coefficient of x is always the slope. In the same spirit, the slope of the regression line of x on y will be, if you're drawing it on the same graph where x is the horizontal axis and y is the horizontal axis, in that case your slope of regression of x on y will be 1 by b times xy, which means it will be sigma y by r times sigma x. This might look a little bit confusing, but remember the criteria that I'm saying is your horizontal axis plots x values and your vertical axis plots y values. In that case, your regression equation x on y is x is equal to a dash plus bxy times y, right? So if I express it as y equals to mx plus c, it will be y is equal to minus a dash plus x whole divided by bxy, which means y is equal to minus a dash by bxy plus 1 by bxy times x. So in this case your coefficient of x is 1 by bxy, which is why I have written this in this manner. Okay, now I have to express it in this form because I'm expressing or plotting all the x values on the horizontal axis and all the y values on the vertical axis. I suggest that you try and plot two related lines on the same graph to convince yourself. Now, the fourth property is that the geometric mean of the regression coefficients is equal to the correlation coefficient. Remember, in terms numerically. Now, do you remember what the formula for geometric mean was? It is the nth root of n observations. Now we have two observations, bxy, or we have two values, bxy and byx. So their geometric mean would be the square root of the product of the two. And we had shown that the product of the two is r square. So the geometric mean would be plus or minus r. So numerically, your geometric mean will be equal to the correlation coefficient. In terms of sign, it depends on which square root, positive square root or negative square root, that you're taking into consideration. So that was the fourth property. And the final property is that the regression coefficients are independent of origin. But dependent on the scale of measurement. So those are your 5 properties. And I think we can wind up this section on regression by drawing your attention to the differences between regression and correlation. Now, I have mentioned this off and on during the last few lectures, but let me just discuss it once more. The first difference is that correlation assesses the degree of association between two variables or two or more variables. So are they moving in the same direction, or are they moving in the opposite direction, and how much together they are moving. Regression, on the other hand, shows an average relationship between the two variables. So that's the first difference, regression and correlation. So correlation is a measure of degree of association, and regression is a measure of, or is an average relationship between the two variables. Correlation need not imply cause and effect relationship, whereas regression regression analysis clearly indicates a cause and effect relationship. Right? You regress x on y or y on x depending on which you consider to be the causal factor and which you think is the effect that is observed. So whereas correlation measures the degree of relationship, regression has a look at the nature of the relationship between the two. The coefficient of correlation is a relative measure, whereas regression coefficients, although the term coefficient does enter, are absolute measures of the relationships. It is possible that you have spurious correlation. This is also known as nonsensical correlation, that is, two variables might appear to be associated to a high degree even though there is no logic behind the association. Whereas we rarely come across something called nonsense regression or spurious regression, right? Correlation cannot be used for further mathematical manipulation or mathematical treatment, whereas the regression coefficient is widely used for further mathematical treatment. In particular, we do a lot of inference testing and confidence interval building and so on with the correlation coefficient, regression coefficient. And the seventh one, the regression coefficient will not differ whether x depends on y or y depends on x. But we cannot say that for regression. In regression, we are estimating a functional relationship between x and y. So whether it is changes in x that is affecting y or whether it is changes in y that affects x is very important and mean very different things. So we have to be clear as to which variable has to be treated as the independent variable and which variable has to be treated as a dependent variable. This is also in statistics and in econometrics we call it asymmetric handling of the variables, whereas in correlation they are handled in a symmetric manner, that is, both are considered similar and to be of similar nature. In regression, depending on which is the explanatory variable and which is the dependent variable, the nature of the variable itself is treated differently.